this lesson, we'll revisit the problem of portfolio construction, computation of expected returns, risk, correlation, and covariance. We'll also summarize our learnings of portfolio optimization with two security case and multi-security case. We'll construct portfolio possibility curve and examine the feasibility region where all the possible combination of securities in the form of portfolios are available to investors. We'll examine various properties of this feasible region with and without short sale and minimum variance portfolio. We'll try to find the most efficient portfolio on these available set of portfolios. Subsequently, we'll introduce risk-free lending and borrowing and examine the implication of the efficient set of portfolios. Lastly, we'll introduce the concept of market risk and beta. Portfolio construction recap 1. In this video, we'll discuss the expected return, risk, and correlation structure for a multi-security portfolio. The actual return on a portfolio of assets for any given period is the weighted average of the actual return on the individual securities for that given period. The weights are the fraction of the portfolio invested in securities. Now we'll try and compute the expected returns of the portfolio. But what is the need to compute the expected returns? Because it is the expected returns that are matched with the risk profile in various portfolio applications, not the actual returns. Now, keeping this rule in mind, we know that expected returns on any security for any period are the simple average, if all the return observations are equally likely, of the returns sampled from the past periods. What does it mean and what are its implications? This simply means the following. If you have three observations, for example 10%, 20% and 30%, and also that the returns on a security are sampled in an unbiased manner over equally spaced periods like daily, weekly and so on, then the expected returns for any given period are the simple averages, for example 10 plus 20 plus 30% divided by 3, which is equal to 20%. Mathematically, this can be very easily written as return Ri bar, which is the expected returns, equal to 1 upon t, summation t equal to 1 to t, RIT. Now, consider the actual return on a portfolio for period t, as shown here. RPT equal to summation xi RIT over I equal to 1 to n, where I depicts one of the n securities and xi is the weight invested in the security I. Now, the expected returns of the portfolio can be easily written as RP bar equal to expected RPT or expectations of xi RIT summation over I equal to 1 to n. This can be also written in the following manner. Summation of I equal to 1 to n expectations of xi RIT or summation of I equal to 1 to n xi times expectation of RIT, because xi is constant, and this can be effectively written as RP bar equal to summation I equal to 1 to n xi times Ri bar, as shown here in equation 2. Even if you are not comfortable with the derivation above, keep the last result in mind. In simple English, this result suggests that the expected returns on the portfolio are simply the weighted average of the expected returns on the individual securities. Here, the weights are the proportion of the portfolio invested in the securities. Please note that while equation 2 looks similar to equation 1, there is a fundamental difference. Equation 1 describes the relationship between the actual return on portfolios and individual securities in that portfolio, while equation 2 describes the expected returns. Now let us talk about computing the risk or standard deviation for a portfolio of assets. Now that we have understood the return part, we'll move to the risk part. However, it is not so simple for a multi-security case, so we'll start with the two securities case with returns being R1, R2. Therefore, sigma p square is equal to expectation of RPT minus RP bar raised to the power 2, which can be further expanded with expectations of x1 R1t plus x2 R2t minus x1 R1 bar plus x2 R2 bar raised to the power 2, which is also equal to expectation of x1 times R1t minus R1 bar plus x2 times R2t minus R2 bar raised to the power 2. This expression can be further expanded to sigma p square times expectation of x1 square times R1t minus R1 bar square, then x2 square R2t minus R2 bar square plus 2 times x1 x2 R1t minus R1 bar square into R2t minus R2 bar, which can be further simplified like this: x1 square times expectation of R1t minus R1 bar raised to the power 2, x2 square expectation of R2t minus R2 bar raised to the power 2 plus 2 times x1 x2 expectation of R1t minus R1 bar into R2t minus R2 bar. This third term here, which is denoted as expectation of R1T minus R1 bar into R2T minus R2 bar, is also called the covariance between securities 1 and 2, and it can be easily depicted as sigma 1 2, which is the covariance between security 1 and 2. And please note a very fundamental property, that sigma 1 2 equal to sigma 2 1. Also, we must notice that this expectation of R1T minus R1 bar raised to the power T 2 is nothing but sigma 1 square. This is by definition sigma 1 square. Similarly, expectation of R2T minus R2 bar raised to the power 2 is nothing but sigma 2 raised to the power 2. Therefore, our resulting expression can be written here. This is our resulting expression of risk for the two security portfolio, that is sigma p square equal to x1 square sigma 1 square plus x2 square sigma 2 square plus 2 times x1 x2 into sigma 1 2. Now this expression can be further extended for a 3 security portfolio, and here it is sigma p square plus x1 square sigma 1 square plus x2 square sigma 2 square plus x3 square sigma 3 square plus 2 times x1 x2 sigma 1 2 plus 2 times x1 x3 sigma 1 3 plus 2 times x1 x3 sigma 2 3, which is very simply an extension of 3 security case. Let us have few words on the covariance. Please note that this covariance is a product of two deviations. For example, as you can see here, it is the expectation of R1T minus R1 bar into R2T minus R2 bar. Since the deviations are from two different securities, unlike the variance, we may expect it to be negative as well, though that is a less practical scenario. If both the securities move together, that is large positive outcomes and large negative outcomes are observed for both of these securities together, then the covariance is expected to be high and positive. Conversely, if large positive outcomes of one security occur together with the large negative outcomes of the other security, then the covariance is expected to be high and negative. If the two securities do not move together, then the covariance is expected to be low. This covariance between security I and K is standardized in the following manner to obtain the correlation coefficient as shown here. We simply divide the covariance between security I and K, that is sigma ik, by their respective standard deviation sigma and sigma k to obtain the correlation between these two securities rho ik. Here we have simply divided the covariance by individual deviations, standard deviations, to obtain the standardized measure, which is also known as correlation coefficient. This correlation coefficient is very easy to interpret and it is free of any scale bias. It varies between +1 and -1. To summarize, in this video we discussed the expected return, risk and covariance of securities in a portfolio. We also discussed that covariance can be standardized to obtain a more clean measure of correlation between securities in a portfolio, and this measure ranges from +1 to -1. Portfolio construction recap 2. In this video, we'll talk about the risk of a more generic N security portfolio case. Now, moving to a more generic case of N securities, while solving these cases requires computer programming, however, a small discussion will hurt nobody. If we carefully examine the terms in the equation 4 shown earlier, we'll find that these terms can be segregated into two categories. Terms that are similar to x1 square sigma 1 square. For example, you can see here in the 3 security case, you have sigma p square as x1 square sigma 1 square plus x2 square sigma 2 square plus x3 square sigma square. These are the terms. And another set of terms like 2 times x1 x2 sigma 1 2, 2 times x1 x3 sigma 1 3, and so on. Terms like x1 square sigma 1 square, these are called variance terms, and terms like x1 x2, these are called covariance terms. Now for N security variance, the generalized term can be simply written as xi square summation of xi square sigma square I equal to 1 to n. Let us confirm the correctness of this term by applying it for 2 or 3 security case or even more. A 3 security case is already provided here, as we can see. Understanding the second term, which is the covariance term, is slightly more involved. The term looks like this. It is summation of j equal to 1 to n, summation of k equal to 1 to n, xj xk times sigma jk. Please note, this j is not equal to k. For all the cases where j equal to k, it becomes the variance terms. If you are looking for the coefficient of security 2, which is multiplied with all the covariance terms, please remember that j equal to 2, k equal to 3, and j equal to 3 and k equal to 2 will give the same two results, that is sigma 2 3 equal to sigma 3 2, and that is why we have a multiplication of 2 here. So this would have been x1 x3 times sigma 1 3 plus x1 x3 times sigma 3 1, and that is why summation of these two will become 2 times x1 x3 sigma 1 3. Also, the symbol j is not equal to k ensures that the k is not the same as j, which otherwise would result in the variance term. So now we can write the full equation for the generalized n security case very simply as follows: sigma p square equal to summation I equal to 1 to n xi square sigma I square plus summation j equal to 1 to n times k equal to 1 to n xi xj xk xjk, j is not equal to k. Let us examine this formula further. Assume that we are investing equal amounts in each of these securities, and in that case, x1 equal to x2 equal to xn equal to 1 upon n. This means that the variance terms will become 1 upon n squared summation I equal to 1 to n sigma I square, or we can take 1 upon n outside to make it 1 summation I equal to 1 to n sigma I square upon n. The term summation of I equal to 1 to n sigma I square upon n represents the average of variances or average variance, that is sigma I bar square. So we can write this term as sigma I bar square, sort of average variance. And thus the summation of the variance term can also be written in the form of average variance as sigma I bar square upon n. This is average variance multiplied by 1 upon n. So for a portfolio with large number of securities, this variance term will become close to 0 or very small. As n increases, this overall term or summation of variances will become very small. In fact, if you assume n tends to infinity, this term will become close to 0. What about covariance terms? Summation of covariance terms. Since there are n securities, there will be n into n minus 1 covariance terms. For example, with 3 securities, there will be 6 such terms. However, since half of them are the same, that is sigma ij equal to sigma ji, we use a multiple of 2 and only 3 terms are left. Therefore, if we present the covariance terms like this, that is j equal to 1 to n summation into k equal to 1 to some n summation n xj xk sigma jk, which is equal to ultimately summation of j equal to 1 times k equal to 1 to n into 1 upon n square sigma jk. This also assumes equal investment in all the securities. That means x1 equal to x2 and so on equal to 1 upon n, equal investments. And this can be further simplified like this: n minus 1 upon n into summation j equal to 1 to n into summation k equal to 1 to n times 1 upon n to n minus 1 times sigma jk. The term j equal to 1 to n times k summation k equal to 1 to n into 1 upon n to n minus 1 times sigma jk is the summation of covariances divided by the number of covariances. Remember, there are n into n minus 1 covariance terms. So this is also called the average covariance or sigma jk bar. Thus, all the covariance terms can be denoted using the average covariance term as n minus 1 upon n into sigma jk bar. In this case, please note, as much as you can increase n, this term will approach to unity. So if n tends to infinity, this term will approach to 1. And therefore, the resulting variance or summation of all the covariance terms will approach sigma jk bar, which is precisely the average variance covariance term, and it is not equal to 0 as happened in the case of variances. So this summation of all the covariance term with a very high value of number of securities, this approaches average covariance sigma jk bar. So what happens to the overall risk of the portfolio, that is summation of variance terms plus covariance term when we have large number of securities? So look at this overall total standard deviation of the security portfolio. It converges to sigma p square equal to 1 upon n times sigma I bar square, which is the average variance, plus n minus 1 upon n times sigma jk bar, which is average covariance. Now please note, for a very large number of securities, that is n increasing to a very large number, this term will approach to 0 or a very small value, and this n minus 1 upon n will approach to unity, and therefore we can say that sigma p square will simplify or approach to this value sigma jk bar. This is precisely what we observe in this diagram. Let us discuss this diagram in slightly more detail. The diagram gives us the intuition that as the number of securities are increased, as you can see here, the number of securities are increasing, the variance term that represent the risk of the security is offset. For example, here till here you have the variance term component, and here you have covariance component. As the number of securities are increased, this variance term drastically decreases, and for even a small number of securities like 30, it becomes close to 0. So what is left is the covariance risk that cannot be diversified away. That means this is also called the bedrock of risk, as we discussed earlier. And as more and more securities are added, as figure shown here depicts how the specific risk or the variance term, this variance term dies away, and only the covariance risk, this risk remains. These are the covariance terms that are left to contribute to the risk of portfolio, or the average covariance. With a fairly large number of securities, this remaining risk is equal to the average covariance of the portfolio, often called as market risk or systematic risk or non-diversifiable risk. To summarize, in this video, we discussed the risk or standard deviation of an N-security portfolio. We found that as the number of securities increase, the variance term or the idiosyncratic stock specific risk is eliminated, and the only risk remaining is non-diversifiable and is on account of covariances, which is driven by correlations across securities. This is the benefit of diversification. Simply by adding more securities to a portfolio, we are able to eliminate the stock specific idiosyncratic risk. Mean variance framework. In this video, we'll introduce the Harry-Markowitz mean variance framework and its role in portfolio optimization. Since 1952, Harry-Markowitz seminal work on portfolio selection, the practice of portfolio diversification is well known and documented. In short, by choosing stocks that do not move together or with low correlation, investors can reduce the standard deviation of portfolio returns. If a sufficiently large number of past return observations are taken, their distribution is plotted, then this distribution is fairly close to a normal distribution that we saw earlier. Though there are certain issues at tail, for example, there are observations related to extreme positive and negative values that may cause deviations from the normal distribution, and other issues such as excess kurtosis and fat tails. The normal distribution is considered to define the return distributions very well and uses only two particular parameters, which is mean and standard deviation or variance. In a nutshell, all the past returns can be defined by these two numbers, that is mean and standard deviation, and that is the reason we have discussed the normal distribution in some of the previous discussions. Now let us combine two securities to construct a portfolio. Consider two securities A and B. Security A offers 8% expected return and B offers 18.8% return. Standard deviation of A is 13.2% and that of B is 31%. A portfolio comprising these two securities has its expected return and risk governed by these two equations, equation 1 and 2, which can be seen here. For example, expected return of the portfolio can be easily written as W1 times R1 bar, which is the expected return on security 1, and W times 2 times R2 bar, which is equation 1 for expected return on the portfolio. This we have seen earlier. Similarly, the variance of the portfolio is W1 square sigma 1 square plus W2 square sigma 2 square plus 2 times W1 W2 rho 1 2 into sigma 1 sigma 2. This equation 2, which also we have seen earlier. Now we'll examine all the behavior of returns and standard deviation for different levels of correlations and different investment proportions, that is W1 and W2 for these two securities. We have plotted all the possible portfolios of correlations corresponding to rho equal to 1 in blue, rho 1 2 equal to 0.5 in red, rho 1 2 equal to 0 in yellow, and rho 1 2 equal to minus 0.5 in green, and rho 1 2 equal to minus 1 in black. Here, each curve with a given color indicates all the possible combinations of investment. That is, each possibility is a point here in either of these securities from W1 equal to 0 to W1 equal to 1, where W1 plus W2 equal to 1. So basically we are varying the proportionate amounts, that is W1 and W2, between 0 and 1, and ensuring that W1 plus W2 equal to 1 constraint is followed. These graphs are essentially governed by the two return and risk equations that we have already seen, which is Rp equal to W1 R1 plus W2 R2, and sigma p square is equal to W1 square sigma 1 square W2 square sigma 2 square plus 2 times W1 W2 sigma 1 sigma 2 rho 1 2, the equation 1 and 2 that we saw earlier. Rho 1 2 here was the correlation coefficient between the two securities 1 and 2, and then a very important parameter. Now please consider the blue line here with rho 1 2 equal to 1, a correlation. In this special case, the equation becomes a straight line with sigma p equal to W1 sigma 1 plus W2 sigma 2. This is the blue line case, this case. And it should be clear from the graph itself that across all the graphs, the lowest amount of diversification, that is highest portfolio risk sigma p square, is achieved for a given level of return associated with this line. Why so? Please notice that for this blue line, for all the combination of W1, W2, the amount of risk for a given level of return is maximum for all the combination. For example, if we look at this level of returns, the maximum risk is obtained on this blue line for all the different correlation combinations. The minimum correlate, we'll discuss the minimum and other combinations also, but it is very easy to see here that the maximum risk is observed or obtained for this particular line. And in this particular line, there is no diversification, and the equation of risk sigma p is simply the weighted average of risk between two securities, that is W1 times sigma 1 plus W2 times sigma 2, something similar to the weighted average of returns as we computed. Next, we examine the other extreme case corresponding to rho 1 to equal to -1, and that correlation is shown here in green. This is the case where highest diversification is observed as it carries the highest levels of return for a given level of risk or minimum level of risk for a given level of return. In this case, the equation for risk effectively becomes or described by this equation, which is sigma p square is equal to W1 sigma 1 minus W2 sigma 2 raised to the power 2. Please remember, this particular equation has two solutions, each representing a straight line. That is, line number 1 is sigma p equal to W1 sigma 1 minus W2 sigma 2, which is this line, and W1 sigma 1 minus W2 sigma 2, which is this line. So in this case, when sigma p equal to W1 sigma 1 minus W2 sigma 2, when W1 into 1 sigma 1 minus W2 sigma 2 is greater than equal to 0, and sigma p equal to minus W1 sigma 1 minus W2 sigma 2 when W1 sigma 1 minus W2 sigma 2 is less than 0. So these two line segments can be represented by these, first this black line and the other one is by this black line. So these are two line segments, and these two lines intersect at sigma p equal to 0, where precisely W1 equal to sigma 1, W1 sigma 1 equal to W2 sigma 2. Now this is a very special but an impractical case where you have attained complete diversification with zero risk. Such cases of negative correlation are rarely observed and almost okay from theoretical point of view, but not observed practically. However, if we assume them to be true in theoretical sense, then there is a possible combination of weights W1 and W2 such that we can obtain this condition W1 sigma 1 equal to W2 sigma 2, and the risk of the portfolio, such hypothetical portfolio, complete risk becomes 0 or neutralized. This is a special case where minimum risk sigma p equal to 0 is observed. For all the other cases where rho 1 2 lies between -1 to +1 are concave kind of curves in between these two lines. For example, notice all the cases will be between this blue or black line. You will not observe any case such as this. Such cases will not be observed. So all these are concave kind of cases between blue and black line, the extreme cases that we have discussed. Any point here would suggest even higher level of risk for a given level of return as compared to maximum correlation rho equal to 1, which is not feasible. And any point beyond this black curve would suggest a risk which is lower than even this negative -1 correlation, which is also not possible. So all the possible combinations are expected for different correlation levels are expected to lie only between these two black and blue curves and of concave nature. So there are no convex cases like this outside, which would be outside, as the lines will strictly lie between these two extreme cases of black and blue lines. Also imagine a concave curve. It would suggest a completely opposite situation to what we have discussed about diversification. It would suggest the existence of curves where expected returns will be lower for a given level of risk, as we have considered portfolio of securities. It would suggest more risk here. If it is of this nature, it would suggest, if the curve is of this nature, it would suggest more risk for a given level of return or less expected return for a given level of risk, which is spurious and not possible. So our region of possibilities is strictly lined between this black and blue lines. So this is the region of possibility for all possible combination of correlations and W1 W2 weights. An important observation here is that the risk of the portfolio for a given level of returns is sometimes even less than the least risky security in the portfolio. So the risk is sometimes even less than, for example, this is the least risky security, then there are certain combination where risk is even less or on the left of it. And this is particularly the case when the correlation between the securities is very low. For example, on this side where correlation is low, on this side we are expecting low correlation points. In actual terms, there may be a security that exhibits returns outside this region of possibilities. Then what happens? Surely expectations cannot stay away from the actual returns for a long time if markets are reasonably efficient. That means if any security is lying outside of this feasibility region, then market forces of arbitrage and market efficiency will drive down these points or these returns back to the normal levels by correcting the points. So there will be a correction witnessed in the point that will drive down the observed level of prices to align them with the expected returns. So we have seen that adding more and more securities to the portfolio here surely lowers the specific risk of the portfolio. Even with 15 to 20 stocks, we can achieve a considerable amount of diversification by neutralizing the stock specific or variance risk. What happens when we add more and more securities to this two stock portfolio? How does the feasible region, as we saw here earlier, this region changes, which is the area of all the possibilities. In the next video, we'll discuss these possibilities when we add more securities to this two stock portfolio, how this feasibility region changes. To summarize, in this video, we saw the mean variance framework of Harry Markowitz. We found that for a correlation equal to 1, there's no diversification in risk, and the total risk of the portfolio is simply the weighted average of individual risk or standard deviations of the two securities, weights being the proportionate amount invested in these. We also saw that for a theoretical and hypothetical case where correlation is strictly equal to -1, maximum diversification is achieved, which is represented here by two line segments in the black color. Theoretically, there is a possibility of a point where overall risk becomes 0 for a given correlation equal to -1. However, that is more of a theoretical possibility. For all the possible combinations of correlation and proportionate amounts invested in the portfolio, the feasibility region lies between these two curves, that is between this blue, which is corresponding to sigma equal to correlation equal to 1, and the black curve, which is corresponding to correlation equal to -1. So all the feasible points lie in this region. Any other points that are outside this curve, whether on this side or this side, are not possible. And if there is a stock for which prices are such that the stock lies on this point, market forces of arbitrage and market forces of efficiency will drive that point or price of that security within this region in a short frame if the markets are reasonably efficient. Portfolio possibilities curve. In this video, we'll talk about the feasible region and various portfolio possibilities with multi-security case. We start with 4 hypothetical portfolios. Different combinations of ABCD, that means ABCD, AC, and so on, with different investment mixtures can lead to a large number of portfolio possibilities as shown here. These possibilities are shown in the form of curves in the figure. As we add more and more securities, we get the first diagram like a net cut shape. As we keep on forming these combinations infinitely, we can add more and more securities, and in addition to these sort of securities, we'll get the convex egg cut shape as provided here. This region of possibilities is shown here in blue. The blue area is effectively the region of expected return and risk possibilities that an investor can attain. Each point here represents a combination of risk and returns that is available to investors in the form of investment into portfolios. Together, all these points or portfolios comprise region of possibilities or the feasible region, as we can see here. This is your feasible region of all the possible different combinations. We started from 4 securities A, B, and C and D. Then we kept adding more and more securities to obtain this region of possibility. Now, on this region of possibility, our goal is clear. We want to move up or increase the returns. That means we want to move in this direction, where for a given risk, we are increasing the expected returns. And we want to move to left. That means for a given level of return, we want to reduce the risk. As we do this, we reach the top surface of region of possibilities, which is this surface, or we can say SS dash on this region of feasibility. There are no more points where we can move further left or up on this curve. So this is the extreme available to us, the best possible combination. And that is why this region is called efficient frontier. All the points on this region offer the highest return for a given level of risk or lowest risk for a given level of return. For example, if you pick this level of return, the lowest amount of risk available for all the points available in feasible region would be on this, that is on the surface SS dash. Similarly, if you pick a level of risk, let's say this level of risk, the maximum level of return available would be on this SS dash line here. Now on this SS dash or efficient frontier, each investor, depending upon their risk preference, may choose a specific risk level. For example, investor may choose this point if he prefers this level of risk, or if he prefers a lower level of risk, they can move left or left on this particular efficient frontier. Once the investor decides a specific risk level, they will have a given level of fixed return on the surface SS dash. So we hope, and we can clearly see here, that once the investor reaches this surface of risk return, they cannot do any better by moving left or up. Now, if you focus on this efficient frontier, which is SS dash, 2 points are particularly important for us here. First, point S. This point is the minimum risk point. So if you look at this efficient frontier on the feasible region, this point has the minimum risk. There is no point on the left of this in the feasible region. So this is the leftmost point and therefore represents the point of minimum risk. Similarly, point S dash, which is at the top of it, is the point of maximum return. So there is no point on this feasible region which is above this point S dash, and therefore this point offers you the maximum return. All the combinations of this surface SS dash are called efficient frontier on this entire feasible region, because these points offer you the best combinations of risk and return possible in the entire feasible region. So this becomes our efficient frontier. One interesting point to note here or observe, that if you go below this point S, there are some points that offer you lower return, but these points are not efficient, because for this level of return you can also obtain this level of risk, you can also obtain this level of return. So as compared to this point, you would like to be on this point. So in this manner, the SS dash remains the efficient frontier, the best combinations of risk return that are available to you. To summarize, in this video, we saw that as we keep on adding multiple securities to a portfolio, we obtain a region of possibilities which is called feasible region, as shown here in the blue. This appears to be an egg cut shape. In order to improve our position or profile on this feasible region, we would like to move on the left to improve our or lower our risk for a given level of return, or we want to move up to increase our expected return for a given level of risk. As we keep on doing that, we obtain a region called efficient frontier, or a surface which is efficient frontier, which offers us the best possible combinations of risk return scenarios. And this surface or this region, which is called efficient frontier, starts from the point with the minimum risk, global minimum risk portfolio, which is S here, and the portfolio which offers the maximum expected return, S dash here, and this SS dash presents as the efficient frontier. Feasible frontiers. In this video, we'll examine the shape of efficient frontiers that are feasible. We'll also discuss some of the shapes of efficient frontiers that are not feasible. Look at the possibility curve shown here. From what we already know, the figure B is not a possibility because it is convex in nature. Notice the convex nature of figure B here. We already know that there cannot be points to the right of this line joining MB and C. We know that there cannot be any points to the right of line joining global minimum variance portfolio, which is MV, and C here, which is above MV. Why so? Because for any point that lies on this curve, we'll have a risk which is higher than those points that have perfect correlation, which is equal to 1, that fall on this line. And therefore, in that case, the points on the convex curve will have more risk or higher standard deviation than the straight line. But we already know that the straight line joining MB and C corresponds to the highest risk, which is correlation equal to 1, and hence it is not possible. What about figure C? This figure. Please note, again, our reasoning remains the same. U and V are also portfolios. So any portfolio that can be formed by combining U and V would look something like this. And therefore, any shape which is like this, convex shape like this, should not be possible. So the straight line joining this UV points will be one extreme set of portfolios with the highest risk. And therefore, the shape of the curve joining UV can only be at max or at best a straight line or a concave curve, not this kind of convex curve as we have discussed. And therefore, this figure C is also not a possibility. Let us also now discuss the points that are below the minimum variance frontier, like here shown in A, B, and C. With the same reasons as we discussed earlier, only A is the feasible option. This one is the feasible one. The curve below the point MV should be convex like this. And therefore figure B is also not possible because it would again represent those points that are having higher risk than this straight line with correlation equal to 1. Now if U and V are combinations of MV and S, for example these U and V, they are combination of MV and S. If the portfolios U and V are mixed, the combination can be a convex curve at or max a straight line joining UV like this. So it can be like this or the straight line joining there. It cannot be a concave curve as shown here. So it cannot be a concave curve, and therefore C is also not a possibility. So now we have understood the risk return profile of a combination of two assets and how feasible frontier would look like. To summarize, in this video, we discussed the shape of feasible frontiers. For those points that are lying above the minimum variance portfolio MV, this MV, the shape of efficient frontier should be a concave curve that is towards the left of the straight line joining point MV and S, which suggests that there cannot be any portfolio with higher risk for a given level of return. Similarly, for those points that are below MV, the curve has to be convex and not concave. The shape of feasible frontier should be convex, not concave, because all the concave curves would indicate those points that have higher risk for a given return than the correlation equal to 1. Efficient frontier scenarios, multi-security case 1. In this video, we'll talk about different efficient frontiers for multi-security case, first without short sales and then with short sales. Let us start by examining a case with multiple securities that are distributed in a rather heterogeneous manner as shown in the figure here. So here we have 6 securities. These are A, B, C, D, E. These 6 securities, they are different combinations are plotted here on risk and expected return space. Before we start our discussion, let us remember two important goals. One, higher return for a given risk, that means for a given amount of risk, we would like to have higher expected returns, that is, we would like to move up, and lower the risk for a given level of return, that is, we would like to move on the left. These are desirable portfolio characteristics. Now, if we compare portfolios A and B here, portfolio A and B, in this possibility space, which is this portfolio possibility space, B of course would be preferable to A, since it offers a higher return for the same level of risk, as we can see here. Similarly, C would be preferable to A because it offers same level of return with lower level of risk. So it may appear to us by this logic that no portfolio dominates portfolio CB, or for that matter portfolio E. So these are the dominating portfolios. This kind of elimination process, where we compare the portfolios for their risk return profile, we can easily see that portfolios CBE, they cannot be eliminated, and therefore they are part of the efficient frontier. Also, we can clearly see here that C is the point of global minimum variance. That means there is no portfolio that has lower risk that is on the left of this point. So no point on this feasibility region is on the left of point C. So no other portfolio has a lower risk than this portfolio C. And therefore we can say this surface CEB would comprise the set of portfolios that offer the highest return for a given level of risk, or alternatively the lowest risk for a given level of return. Therefore, this curvature, the set of portfolios that lie on this curvature CEB, are called efficient set of portfolios, or this is our efficient frontier. Here we also find that this C portfolio is the portfolio with minimum variance, and portfolio B is the portfolio with maximum return. Also, we can call C as global minimum variance portfolio. Now, if we take out the portion of this efficient frontier, it would look something like the graph shown on A, this A curvature. We know from our previous discussions that the shape can only be concave, not convex. The lower end of this frontier represents the portfolio with the minimum variance, this one, the minimum variance. The higher end of this portfolio is the portfolio with maximum return across all the portfolio, that is security with the highest returns. Please remember, in this case, we cannot have a portfolio looking like B, as we have discussed already. Any convex nature like between U and B is not possible. Why? Because you and we are also portfolios, and therefore we have already discussed, if all the points are above minimum variance frontier, that is above this minimum variance point, any two portfolios, you and V, their combination can be at best a straight line, and in that case this straight line would represent portfolios with correlation of 1, that is maximum risk. So any portfolio on the right side of it would represent a set of portfolios that carry higher risk than those with correlation of 1, which is not possible, and therefore any set of portfolios on the right side would not be possible, and therefore this convex nature of curve is not possible. Therefore B is not a feasible scenario. The only feasible scenario for efficient frontier in this case is this one. Now let us talk about a case where short sales is allowed. Short sale is essentially selling a security one does not own, which is equivalent to taking a negative position in a security. This negative position allows one some additional liquidity or funds that one can invest further in taking a long position or investing in any other purposes. Now, if you are making the short selling, you would like to sell securities that have lower expected returns, and you would like to buy securities from those proceeds where you have higher expected returns. And therefore, those not so efficient securities which are lower in the efficient frontier, here you have this opportunity now to short sell these securities because these securities are offering us lower expected returns. This suggests that one can keep on short selling securities that are here while investing in long in securities that are here and extending their position beyond B to C and further high. Theoretically, this suggests that one can achieve infinite expected returns or very large amount of expected returns, but at the same time, when you do that, you also extend the risk of your position, that is, you also extend the risk or standard deviation to very large levels. And therefore, one can see that now our actual efficient frontier is not restricted at point B, and one can take positions that can go beyond B and even further and further. So now on aggregate, our position becomes MVB and beyond to C. So one can extend their portfolio possibility curve to MVBC, which becomes the new efficient frontier. And notice that this is a concave curve, which is similar to earlier without short sale scenario, but now with short sales, our efficient frontier extends from MV. Not only it moves up to the security with maximum return, but it also extends beyond that to large expected returns which have no finite upper bound. However, please note the caveat: in order to achieve that, we are assuming a large amount of short sales. Every market have certain restrictions on short sales, but still, to a reasonable extent, we can assume that one can extend their efficient frontier beyond this point B, which was point of maximum return, to further with no upper bound. To summarize, in this video, we discussed the shape of efficient frontier with and without short sales. We found that in the absence of short sales, the efficient frontier extends from portfolio of minimum variance, a portfolio with global minimum variance, to portfolio of maximum return, in this case MV to B. However, when the restrictions on short sales are removed, one can short sell securities with poor expected return and invest them in higher expected returns that are on efficient frontier and extend their possibilities beyond this upper point B. And in that case, the expected returns would be very higher with no upper bound on this efficient frontier. However, at the same time, if one were to obtain such positions, the risk or standard deviation of such positions would also be very high. Efficient frontier scenarios, multi-security case 2. In this video, we'll discuss the shape of efficient frontier with multi-securities and introducing riskless or risk-free instrument. We'll discuss 3 cases. First, efficient frontier with riskless lending and borrowing. Then only riskless lending is allowed, not borrowing. And then riskless lending and borrowing at different rates. As we can see, we gradually move in a step-by-step manner towards a more realistic assumption of different riskless lending and borrowing rates. Up until this point, we were focusing on risky securities. The addition of riskless securities considerably simplifies the analysis, as we'll see now. Here, we are assuming the same rate for borrowing and lending, that is RF, in the first case, which is this RF, same lending and borrowing interest rate. Because the return on these securities is certain, whether it is borrowing or lending, practically this does not happen. Borrowing is often at higher rates than lending. However, for analysis purposes, let us consider the same lending and borrowing rates for now. Now here the intercept is RF, this risk-free rate becomes our intercept, and if you pick randomly any point A on this efficient frontier, then the slope of this line would be RA bar, which is my expected return on RA, minus RF upon sigma A, which is the standard deviation of or risk of security A. This is often referred to as Sharpe ratio also. This RA bar minus RF upon sigma A. RA bar is the expected return on security A and RF is the risk-free rate. The point on the line that is to the left of A, these set of points left to the A till RF, these are the combination of lending at risk-free rate, that means investment in risk-free rate, and investing in portfolio. So a mixture of investment in RF and RA would fall on this line. Conversely, the point on the line that are to the right of A, that means on this side, these are called a combination of borrowing at RF and investing original wealth as well as the borrowed amount in A to result in a position that is on the right of the A on this line segment, and therefore these are called the borrowing segment of the line. However, here we chose the portfolio A randomly with only criteria that it is on the efficient frontier. There may be other portfolios like A, B or G, and the resulting graph may look like this, as we have seen here, like this and like this. Now we have three lines indicating the risk return profile corresponding to three portfolios A, B and G here. These lines extend the possibility region. For example, with line B our possibility region is like this, with A our possibility region is like this, and investors can hold portfolios on these lines joining risk-free rate and points A, B and G. Now the question is, which portfolio is better for us? There appear to be an obvious question. For example, if you look at the points on line RF to B, this RF to B, it offers the higher returns than as corresponding to RF to A. So RF to B offers higher return as corresponding to RF to A for a given level of, for any given level of risk, as we can see here. For any given level of risk, RF to B offers a higher return. Similarly, the points on RF to G offer higher returns than those on RF to B. So this means as we are rotating this line, in the counterclock direction, we are making it steeper and steeper. It suggests that the concept of tangency would indicate the highest we can rotate is up to the point of tangency, which is here point G, as shown here. At this point, the line passing from RF attains the highest slope. Remember that Sharpe ratio, Rg bar minus Rf upon sigma G, the Sharpe ratio. This slope or the ratio would be highest when the point is tangency point, touching the efficient frontier at tangency point. So if the line is further rotated, then there are no portfolios that are in the feasibility region or on the efficient frontier. Therefore, this line RF to G would offer the highest return for any given level of risk as compared to any combination of risk-free asset and investment on any point of this efficient frontier. Therefore, theoretically, all the investors, whether riskless or less risk preferring or more risk preferring, they should all hold this portfolio G. Now, those investors that are more risk averse would invest some of the amount in risk-free rate. Those who are risk averse would invest some amount here on RF and some amount in their portfolio G, so that they are on this segment RFG. This is called the lending segment. Similarly, those investors who are more risk preferring, who would like to take more risk, their portfolio would lie on the segment called borrowing, which is on the right side of G. So they will borrow at this risk-free rate and invest not only their original wealth, but this additional borrowed amount also in the portfolio G. So this is one of the very important tenets of portfolio problem. Here, even if you do not know the investor's risk profile, whether he is more risk preferring or less preferring, once you identify the portfolio G, you can draw a risk return profile for all the optimum portfolios. This is also sometimes called separation theorem or two mutual fund theorem, because we separate the risk profile of the investor from the investment, because we select only two assets. First, a risk-free asset, and second, the portfolio of assets, risky assets called the market portfolio, this portfolio G. And then for all the investors, some combination of RF and G on the lending segment or borrowing at RF and investing in G would create the desired optimum portfolio depending upon their risk preferences. Now let us discuss a special case where only riskless lending is allowed and borrowing is not allowed. This is a slightly more practical case than our previous case, as generally lending at, let's say, government fixed deposits or various other instruments are available at risk-free lending at significantly lower rates. However, borrowing at such lower rates is not available. So once we put this constraint, the segment on the line joining RF to G, this segment RF to G called borrowing is not available. So we have now only lending or this RF to G available, but not on the right side, which was the borrowing segment that is not available to investors. So the now efficient frontier would look something like figure here, RF to G on the straight line, and then from G onwards, this is the efficient frontier. So it is like RFGH. GH is on the right side of RFG, which was part of efficient frontier in the absence of risk-free asset on the right of G. H here is the point of maximum return. In effect, the efficient frontier becomes RFGH. The investment profile of risk-averse investors who are placing some amount in risk-free instrument and some in G, the lending segment, will not change. Only the risk-taking investors will not be able to borrow at RF. They will invest in portfolio on the segment GH. The portfolios on this GH segment are relatively riskier than portfolios on RFG, but these portfolios also offer the higher returns possible at any given risk. So they are offering highest return for any given risk levels. Also, please note that in this case, we need to only identify two risky portfolios, G and H. So once you identify G and H, all the combinations of G and H would lie in between on this curve segment GH. Since all the portfolios on curve joining G and H can be obtained by combining G and H. Lastly, we'll discuss a special case where the riskless lending and borrowing is allowed at different rate. This is a very practical case which we encounter in daily lives. The interest rate at which we borrow is usually much higher than the interest rate at which we invest. For example, you can borrow probably here at RF and invest at RF and borrow at RF dash. RF dash is higher than RF. So the investment profiles for this case is shown here. Now the borrowing at RF dash, which is higher than the lending rate RF, and again for the risk averse investor, the risk return profile remains unchanged. However, the region of borrowing is modified due to higher risk free rate. So the region of borrowing is here. This is the region for borrowing for him, a higher region. Let us say that with the new borrowing rate, the point of tangency is H. So for this RF dash, the point of tangency is H. For the lower rate, the point of tangency is G. So the risk-taking investor have the efficient frontier as the risk portfolios lie between GH curve. So he can invest on GH curve. And after H, the tangent line that joins RF dash to H. So he has this GH curve and then from H onwards. So RF dash H line which extend from this point H. So for risk taking investor, it will be something like this. So this is GH and then line extending, R dash F line extended, R dash F H line extended beyond point H. So effectively your new investment frontier becomes starting from RF to G. So those who are less risk taking, they can probably invest some amount in RF and some amount in G and obtain a portfolio on this in lending segment RFG. And then if you are more risk taking, then your portfolio extend beyond G to H and then H onwards from H to further on this line segment RF dash, which is extended. So your RF, G, H and beyond this line is your complete segment. For those who are less risk taking, they will invest partially in RF and some amount in G, so they will obtain a portion on this RFG portion, they will invest. And those who are more risk taking, they will invest beyond G, G to H on this curvature and then straight line, which is R dash F H extended. To summarize, in this video, we introduce risk-free or riskless instrument with efficient frontier. We discussed three cases. First, with same riskless lending and borrowing rates. Second, unlimited riskless lending but no riskless borrowing. And third, the most practical case that is different risk-free lending and borrowing rates, where risk-free borrowing is at higher rate while risk-free lending is at lower rates. We found that when risk-free asset is introduced, one can find an optimum portfolio which can be available or made available to all the investors irrespective of their choices. For example, we found there was a portfolio G when riskless lending and borrowing rates were same, and a combination of this portfolio G along with risk-free rate can be offered to all the investors irrespective of their choices. Those investors that are less risk-taking would prefer to invest some amount in the risk-free rate and some amount in the risky asset, while those who are more risk-taking, they would like to borrow at risk-free rate and invest further their original wealth as well as additional borrowed amount in the risky portfolio. So these two segments are called lending and borrowing segment respectively. Lending segment for less risk taking investor who is investing in risk-free asset as well as risky asset, while borrowing segment for investors who are borrowing at risk-free rate and invest the borrowed amount and overall wealth into this risky portfolio to obtain a position on borrowing segment. In this video, we'll talk about minimum variance portfolio and some of its interesting properties. In the absence of short sales, 2 points become extremely important on the efficient frontier. First, the portfolio with maximum return, and second, the global minimum variance portfolio. In the absence of short sales, these portfolios define the two extreme ends of the efficient frontier. While it is easy to understand that maximum return portfolio will be the security in the portfolio that offers the maximum return, since the returns are simply the weighted average of returns. The same is not the case with the global minimum variance portfolio. This portfolio is often expected to be different from the security with minimum risk in the portfolio. How do we compute this portfolio? We already know the generic formula for portfolio risk as shown here. The formula is simply sigma p is equal to xa square sigma a square plus sigma b square xb square plus 2 times xa is b rho a b sigma b whole to the power 1 by 2. This is for two security case. Now this formula we can simply compute in order to compute the minima, we need to simply differentiate this expression sigma p, that is d of sigma p. Will not go into the detailed exposition, but we need to differentiate this expression with respect to dxa, and in order to obtain the minima we need to set that this derivative equal to 0 and solve for xa. Solving for xa we'll get something like this, a simple expression like this, which is xa equal to sigma b square minus rho ab into sigma a sigma b upon sigma a plus square plus sigma b square minus 2 times rho ab into sigma a sigma b, where rho ab is the correlation between securities A and B, sigma is the standard deviation of security A, sigma b is the standard deviation of security B, which expression is given by question 3 here. Now let us consider a simple example here. We have been given two securities, stock A and stock B. Stock A has an expected return of 14% and a standard deviation, that is risk, of 6%. Similarly, stock B has expected return of 8% and standard deviation, that is risk of 3%. Now if we assume that the correlation between these two stocks is 0 and we would want to find the minimum variance portfolio for this particular correlation, we need to solve for this expression, and putting rho AB equal to 0 we are left with this term, and given that the risk is for B is 3% and A is 6%, we get this xa is equal to 0.2. Since we already know that xa plus xb equal to 1, we get xb equal to 0.8, and therefore we can compute now sigma p with the expression known to us. Sigma p becomes 0.2 square into 6 square plus 0.8 square into 3 square, which is simply nothing but xa square sigma a square plus xb square sigma b square raised to the power by 2, which is 2.68%. So this is the risk of minimum variance portfolio here. Now let us assume a correlation of 0.5 and then try to compute this expression. Putting correlation as 0.5, we find that xa equal to 0. What is the implication here? Since no combination of securities A and B has less risk than the security B itself, so the global minimum variance portfolio is security B itself. And that is the reason when we compute global minimum variance portfolio here, we get xa equal to 0, which means xb equal to simply 1, which is security B itself. That also means that for any correlation higher than 0.5, the global minimum variance portfolio will be obtained for xa's that are less than 0. Or in the absence of short selling, for all practical purposes, we get xa equal to 0 and xb equal to 1. That means for any correlation that are more than 0.5, the minimum variance portfolio in the absence of short selling will be xb equal to 1 itself, that is security B will remain the global minimum variance portfolio. Now let us assume a correlation of 1 exactly, rho AB equal to 1, and then try to solve this. In that case, when we do that, we find xa is less than 0. In the absence of short selling, which is not a practical thing here, and therefore the limiting constraint that any weight cannot be equal to 0, this gives us x equal to 0 because we are assuming that xa cannot be less than 0. So we are assuming a correlation of -1, and if we assume a correlation of -1, we compute this expression which works out to be xa equal to 1 by 3 and xb equal to 2 by 3. Solving for this, we get xb equal to 0, which is nothing but xa sigma a minus xb sigma b, or wa sigma a wb sigma b, where wa or xa's are the proportionate amounts invested in security a and b. Now this is a special case where rho ab, or correlation between the securities, is equal to -1. However, that is less of a practical case because perfect negative correlations of -1 are rarely observed over long horizons. However, still this is a theoretically important case. Why? Because in this case, we are able to obtain complete diversification. That is, the complete portfolio risk has become equal to 0. So this is a theoretically interesting case where all the risk of the security or portfolio has been diversified. To summarize, in this video, we computed the formula for minimum variance portfolio. We also computed, and through examples, we understood different values of this minimum variance portfolio risk for different values of correlation. We also found that at a particular correlation of -1, the overall portfolio risk can be made 0, and in that case, global minimum variance portfolio risk will become 0 as well. We also noted that it is not necessary, unlike returns where the maximum return or minimum returns are equal to simply the maximum minimum return security in the portfolio. The minimum risk portfolio can have even lower risk than the security in the portfolio with minimum risk. Introduction to risk-free lending and borrowing, part 1. Till now, we have touched upon the use of risk-free instrument in construction of efficient frontier in a more cursory manner. In this video, we'll explore the application of risk-free instrument in efficient frontier construction in more detail. Let us first start by introducing the risk-free lending and borrowing at the same interest rate, that is RF. However, is it practical to assume that risk-free lending and borrowing would be available at the same rate? What are the challenges with this assumption? For example, can you borrow from a government bank like SBI or lend or create fixed deposit with the same bank at the same rate? Is it possible? While this assumption has several challenges, still this assumption has a lot of important implications when it comes to portfolio construction and understanding the efficient frontier. Let us start by assuming a large number of stocks that are used to construct a feasible region of possibilities. You invest in a number of stocks to construct the portfolio, and the feasible region that you will obtain will something like this, the green region obtained here. And you will obtain a very wide selection of risk and return profiles in the form of this feasible region. Now, in this feasible region, you would want to go up in order to increase your expected return for a given level of risk, or you would want to go to left to decrease the risk for a given level of return. And as you keep on doing that, you will obtain this efficient frontier or best set of portfolios that offer you best or optimum combination of risk and return. Mathematically, in order to solve this, you need quadratic programming. This is a sort of capital rationing problem where you have a capital constraint. For example, you may have a capital constraint like xi equal to 1, where xi's are proportionate amounts invested in different securities. And then using this constraint, you would like to solve or maximize your return for a given amount of risk with this capital rationing problem, and you can solve this with quadratic programming. You would need some computer program or software. There are a lot of easily available software packages that can do this. However, addition of riskless securities can considerably simplify our analysis. For example, consider two investments, one in a portfolio of asset A, this risky stock, and another, a risk-free asset may be here. When you have this, then your possibilities improve considerably. There are two segments to this investment. One, if you invest some amount in RF and some amount in A, you obtain what is called lending segment in this region. Generally, a person who is less risk averse would be standing here. Or you can borrow at RF, because we assume that borrowing and lending risk-free rate are same. So you can borrow at RF, invest your own wealth along with any additional borrowed amount in asset A to obtain a position on this borrowing segment. This is precisely the equation of a straight line like y equal to mx plus c, which passes through 2 points. First point is this point A with the expected return of RA bar and risk of sigma A. Another point which is risk-free asset with the expected return of RF and risk of 0 or standard deviation of 0. Let us assume that amount fraction X is placed in the portfolio A, XA. Let's call it X or X. And then therefore remaining 1 minus X amount, because of capital constraint, the summation of XA plus XF should be equal to 1, where XF is the amount invested in risk-free asset, though they should be equal to 1. So the amount invested in risk-free asset is 1 minus X. And therefore the expected return on this portfolio RP is equal to simply X into RA bar plus 1 minus X into RF. RF is the certain return on risk-free instrument. Again, we can also compute the risk of this portfolio sigma p square very simply, x square sigma square plus 1 minus x square sigma f square plus 2x into 1 minus x rho f sigma f. But please remember here, this sigma f equal to 0 because there is no risk with the risk-free instrument, and therefore the amount is simply say x square sigma square. And if we can assume that, then assuming that sigma f equal to 0, we are left with the portfolio risk, a very considerably simplified expression. Because of this introduction of risk-free instrument, we have only this expression as a portfolio risk, sigma p equal to sigma xa sigma. And we already know that RP can be demonstrated or described with this expression. Using these two, equation 1 and 2, we can further simplify this expression in the form of RP bar equal to RF plus RA bar minus RF bar upon sigma A into sigma p. Now, this is a very simplified form of expression of portfolio expected return and risk. And this equation is precisely the straight line that passes through all the combinations of risk-free lending and borrowing with portfolio F. So if you remember, this was the efficient frontier, and any point A if you have picked here, then this would represent all the points on this line. This expression would provide you with the expected return and risk relationship which passes through this line. All the points on this line will be described by this equation. To summarize, in this video, we saw that introduction of risk-free instrument where risk-free lending and borrowing can be done at the same rate considerably simplifies the analysis of efficient frontier, and we obtain a very simple expression of relationship between expected return RP bar and risk of the portfolio. This is obtained because the risk of the risk-free instrument, that is sigma f, is equal to 0, and because of that assumption we are able to obtain this very simple expression of expected return and risk on the portfolio. This is a more generic expression. Introduction to risk-free lending and borrowing part 2. In this video, we'll try to find whether there is a special case or optimum portfolio with the presence of risk-free lending and borrowing that is dominating or dominant position as compared to all the other portfolios or risky assets. Please remember, as we have this opportunity to invest in risk-free asset, as we saw in the previous video, we can take any position on this efficient frontier. We saw that this brown line represents the most set of efficient portfolios or efficient frontier. And now that we have this risk-free asset, I can pick and choose any point on this efficient frontier and combine it with my risky portfolio and find a number of set of opportunities, a very specific set of portfolios that depend upon the risk-free rate and the position that we are taking on this. Let us find out if there is a particular portfolio on this efficient frontier that offers us the best set of combinations of risk return profiles. It would be easy to understand that if I keep on moving on the counterclockwise, I would find the steepest line to be at the tangency point. Let's call this tangency point as S. Please note, if this tangent line from RF to S is drawn, let's put it with the red line, this tangency line. This line will be the steepest line from RF to this efficient frontier. The slope of this line can be easily defined as RS minus RF upon sigma P, where RS is the expected return on security S, RF is the return on risk-free instrument, and sigma P is the risk of the portfolio, that is S. Now, given the fact that this slope is the highest, this is the steepest line, we can easily say that this line or this position S offers maximum expected return for a given level of risk, and that is true for all the points on this line, that they offer for a given level of risk highest amount of return possible as compared to any other point on this efficient frontier. For example, if I draw another line like this for a point, let's say A, all the positions on this line would be a better combination of risk return. That means higher return per unit of risk as compared to any on this line which is joining RF to A. Often this ratio is called, this ratio RS minus RF upon sigma P is a very important ratio called Sharpe ratio to measure the performance of a portfolio. Now we have obtained a particular portfolio or position which in combination with this risk-free instrument offers us the best or optimum set of positions or a new efficient frontier in fact. So this we can call as a new efficient frontier which is become available to us because of this risk-free rate. There are two particular segments on this new efficient frontier that are very important to us. One is called lending or investing, this one, and other is called borrowing. So this lending segment is preferred by investors with low risk preference, while this borrowing segment is preferred by investors with high risk preference. What do I mean by this? So those that are less risk averse, they would be borrowing at RF and investing their own wealth along with this borrowed amount in S to obtain a position on this borrowing segment which extend from S and beyond on this straight line. While those who are high risk averse and do not prefer risk much, they would invest partially their wealth in RF and partially in S to obtain a position on this segment RFS, which is called lending or investing. Now please remember, this kind of position on lending and borrowing segment is freely available to all, and if this portfolio S is known with certainty, then everybody would be holding this portfolio S. Nobody would hold any other portfolio but some proportion of investment in S and some proportion of investment or borrowing in RF. And therefore, since everybody is holding these two portfolios only, the only set of risky assets are held are that in portfolio S. And therefore, this portfolio S is also often referred to as market portfolio, sometimes denoted by M or sometimes by S. This is a market portfolio which is held by everybody. Why we are making this assumption that financial markets are often considered to be very efficient and competitive. So there's no reason for us to believe that anybody or somebody may have a particular advantageous information over long times. That means everybody will have some similar information and all of them will want to hold the same market portfolio M or what we call S. And therefore the job of investment manager becomes very easy, is to find this market portfolio. Once he has identified this market portfolio of common stocks, he need to mix it with RF depending upon the risk preference of individuals. Those who are risk averse, more risk averse, for them some investment in RF and some investment in S, while those who are more risk taking, some borrowing at RF and the borrowed amount plus own wealth can be invested in S to obtain a position on this borrowing segment. So mixing this market portfolio or this portfolio of S along with risk-free asset in different combination can generate various combinations of portfolios that may suit the taste and risk preferences of different profile of investors. And that is why this is often referred to as two-fund theorem or separation theorem. That means the decision to select this portfolio S is independent of investors' risk preference and risk profile. This is a very important result. So whether investors are risk-taking lions or risk-fearing chickens, they can be provided their suitable instrument just by mixing this one portfolio S along with the risk-free instrument. To summarize, in this video, we saw that when the risk-free instrument is available, one particular portfolio, which is the tangency portfolio, becomes the optimum position for all individual investors, and therefore a fund manager can mix this particular optimum portfolio with a risk-free instrument to provide various combinations of portfolios. This includes portfolios on lending segment for those who are more risk averse, and portfolios on borrowing segment by borrowing at RF and investing all in risky asset to those who are more risk taking. And therefore the fund manager can separate the decision of investing from the risk profile of individual investors. This is often referred to as separation theorem or two-fund theorem. Introduction to risk-free lending and borrowing, part 3. In the previous videos, we have understood the introduction of risk-free lending and borrowing can simplify the analysis considerably, and we find an optimum portfolio that is suitable for all. In this video, we'll understand the implications of that optimum portfolio with the help of simple numerical examples. Suppose the market portfolio that you have identified, the best optimum portfolio S, offers 15% expected return and a standard deviation of 16%. Also, the risk-free instrument available to you offers you a 5% return of lending and borrowing with a standard deviation or risk of 0. Now you are a risk averse investor, therefore you would like to invest 50% of your money into RF, which is risk free, and remaining 50% into a portfolio S. Now what does your portfolio look like? Let us try to find out the profile of your investment with the help of following equations of risk and return. We have seen that the risk of our portfolio would be sigma p equal to x times sigma a, while the expected return of the portfolio is x times RA bar plus 1 minus x into RF. Now let us punch in some values here. So given that our investment is 50% into risk-free instrument and risky portfolio, our resulting expression becomes RF into 0.5 plus RS into 0.5, which is equal to 10%. 5% into 0.5 plus 15% into 0.5, which is 10%. The standard deviation of our portfolio sigma p is equal to 0.5 into 16%, which is 8%. And therefore, at this stage, we are standing on that lending segment of portfolio. If this is the tangency portfolio S, this is RF, then right now we are standing somewhere in the mid of this, which offers us an expected return of 10% and risk of 8%. So this is midway between RF and S. Now consider another investor who is more risk taking in his approach. This risk taking investor would like to rather borrow at RF almost 100%, which is equal to his initial wealth, and invest the total amount, that is 100% of borrowed money plus 200% of his plus 100% of initial wealth, that is overall 200% in this market portfolio S. And therefore we can easily compute the risk return profile of this investor in the following manner. First, his return will be RF into -1. This -1 represents the 100% borrowing, plus RS into 2, which represents 200% investment in market portfolio. The resulting profile becomes 5% into -1 plus 15% into 2, which is 25%. Now this is quite a large return, expected return, that he's getting from his portfolio, a very high return. But at the same time, his risk is 2 times 16%, which is 32%. So while this investor has extended his possibilities and he's obtaining a very high amount of expected return, he's standing on the borrowing segment and his risk has also increased considerably. So his position, if this is the tangency portfolio S, this is RF, then his position is almost here. So while he's getting that higher expected return of 25%, at the same time he's also facing a risk of 32% standard deviation. So we saw whether one is a risk fearful chicken or less risk taking person, or a risky lion, that means a more risk taking person. Both of them will prefer to invest in market portfolio than any other combinations available on the efficient frontiers. This tangency portfolio, what we are calling as market portfolio, and therefore this market portfolio is the best efficient portfolio from all the entire set of investors. For all the investors, this is the best portfolio. And identifying this best portfolio is quite easy. We need to draw a tangent line from the risk-free instrument RF to the efficient portfolio, the original efficient portfolios that we identified. These efficient portfolios, we need to draw a tangent line from this risk-free instrument, and this tangent line will give us that market portfolio. This portfolio offers us the highest risk premium, that means highest value of this Sharpe ratio, which is RS minus RF upon sigma p, or the slope, this Sharpe ratio, or the slope, or the amount of risk premium per unit of risk is offered by this market portfolio is highest, which represents the slope of this line. To summarize, with these numericals, we saw whether an individual is risk preferring person or less risk preferring person. One particular portfolio, which is the market portfolio or tangency portfolio, is the most preferred for all of us. And therefore, a combination of this market portfolio with that risk-free instrument provides us with our required portfolio with the best combinations of risk return. The slope of this portfolio, or the per unit of risk premium for a given unit amount of risk, is best across all the set of portfolios available to us on the efficient frontier. And therefore, this market portfolio or optimum portfolio helps us solve the portfolio problem. Market risk and beta. In this video, we'll talk about market risk and a very important measure of market risk, which is beta, which is the sensitivity of a security to market risk. With the help of a simple example, we'll also try to understand the computation of beta. Usually, market risk is associated with a well-diversified portfolio. This is so because for a well-diversified portfolio, the diversifiable or stock specific risk is eliminated, and only it is the systematic non-diversifiable market risk that matters. For example, a portfolio like Nifty 50 or NYSE index, S&P 500. For such portfolios, only market risk matters. So if a sufficiently large amount of securities are added to a portfolio, the only risk that matters is the non-diversifiable systematic or market risk. What is this market risk? Remember the diagram that we saw earlier. So market risk is the bedrock of risk. There are two components. One is idiosyncratic stock specific risk, let's call it SP, and market risk, which is driven by the correlation across securities. Now, as you keep on adding securities, 0, 1, 2, 3, after sufficiently large number of securities are added to the portfolio, then this stock specific risk eliminated, and it tends to go to very close to zero. Even with 30-50 securities, it can be completely eliminated. While the market risk is not eliminated with this diversification of adding more securities, and it sustains. However, it is important to know when a new security is added to a portfolio, what is the contribution of this security to the portfolio? And this contribution of the security to a portfolio is determined by the correlation of that security with the market portfolio. Market portfolio is a portfolio of stocks that carries sufficiently large number of stocks from the market that represents the market and eliminates most of the diversifiable risk. This correlation between that security and market portfolio is often measured through beta I. This is called beta of the stock, or sensitivity of the security to the market portfolio. For example, if the market moves by 1% up and security moves by 1.5% up, then in that case we will say that the beta of the security is 1.5. Or if market moves by 1% or a particular amount and security moves by exactly the same percentage, let's say in this case 1%, then it is said that security has a beta of 1 and it has the same risk as that of the market. Another interesting case is that a security is insensitive to market. Although it is more of a theoretical case, generally securities move to some extent, some may large, some may small, but they definitely move when market shifts. But theoretically, if a security is not at all sensitive to market, and therefore whether markets move up or down, it does not move, then we say that beta of that security is equal to 0, and that security does not have any market risk or systematic risk. One good example of this would be government securities, because government securities are risk-free and they are not affected by the market risk, or they do not move with the market. So essentially, in summary, this beta represents the sensitivity of the security to market movements, and therefore this beta is a good measure of security's contribution to portfolio risk, because it is not eliminated. When you add the security in the market portfolio, this risk is not eliminated. What about the risk of a portfolio or beta of a portfolio? Mathematically, beta of a portfolio is weighted average of betas of individual securities. For example, if you have a n stock portfolio, 1 to n, then if individual betas are beta 1, beta 2, beta 3 and so on up till beta n, where proportionate amounts invested in these securities are W1, W2 and so on up till Wn, then the beta of the portfolio can be simply written as beta P equal to W1 beta 1, W2 beta 2 and so on up till Wn beta n. So summation Wi beta I is the beta of the portfolio. This is the beta of the portfolio. For example, if you observe that the market has a standard deviation of 20% and you construct a portfolio which has a beta of 1.5, then the standard deviation of this portfolio would be 30%, which is 1.5 times 20%. So in summary, the beta of portfolio is simply the weighted average of betas of individual securities. Now, how to mathematically compute betas of a security or a portfolio? So beta of a security or portfolio I is simply the ratio between covariance of that security and market, which is sigma IM, divided by variance of market. So this formula represents the mathematical computation. It comes from the regression model, as we'll see shortly, but this is the ratio of covariance between the security and market divided by the variance of the market. Now, how to compute betas in real life from the given data? So security returns are regressed on market returns. For example, a security I would be regressed on a market returns, where market can be proxied like indices such as Nifty or NYSE. And in this kind of regression model, the slope of the variable market, that is Nifty or NYSE, is called beta. This computation of beta requires us to understand the regression analysis a little bit briefly. So the model that we are running is y equal to alpha plus beta times x, where y is the return on the security I. It can be any security or a portfolio, and alpha is the constant intercept term here, and beta is the slope of market variable x. Now mathematically, in a regression model, it works like this. You have scatter plot where you have different return observations plotted along two axes, x and y, where x is the security return, y is the market return. So if these blue points represent those observations, then you fit a line using ordinary least square method. Notice, as the OLS works, you try to minimize this error, this difference, sum of squares of these errors. These are error terms, EIs. The fitted line, perpendicular between fitted line and the observed point, you take all these errors, EIs, and you try to minimize the summation of square of these error terms. That is, you try to minimize the summation of these error terms, and when you minimize, in that process you obtain the fitted coefficients. You obtain these alphas and betas by fitting this line, which has minimum squared residuals, and this line is called OLS fit, ordinary least square fit, ordinary least square fit model. In this process, the coefficient beta you get is represented by this formula mathematically, which when translated to our context or our background of market risk becomes sigma IM, which is the covariance between the security and market divided by variance of market, sigma square m. So this is the formula for beta, where it comes from using regression analysis when an OLS, ordinary least square line, is fit between security returns and market risk returns regression. Let us do a simple numerical example here to understand this process. Let's say we have these return observations given to us, and market return observations and security return observations for security 1, let's call them R1, and RM for market returns. First, we'll compute the difference between or deviations from mean, like RM minus RM bar. So the mean of RM is 0.3, so minus 1 minus 0.3 is 1 minus 1.3, and similarly we'll compute deviations for all the observations. Same goes for the security returns. Its average or mean is 3.7. So for example, first observation 3.6 minus 3.7, which is minus 0.1, and similarly we'll compute the deviations for all the points. Then we'll also compute the standard deviation of market, which is deviation squares. For example, square of this term, deviation squares, and then summation of all these deviations will be averaged out by dividing them with the total number of observations, which is 10 here. So we get this 63.01, which is the summation of this upon n. Similarly, we'll compute these multiples, RM minus RM bar into R1 minus R1 bar, to get this number, and then multiply this to get this number, and this multiplied by this to get this number, and so on. We'll get all the 10 R1 minus R1 bar into RM minus RM bar, and then divided by the total number of observations, that it's 10, to get this number. Now the ratio of this is our covariance between security and market, and this is our standard variance of market. If we divide the sigma IM by sigma m square, we get the beta measure, that is 0.08, that is 5.04 divided by 63.01, we'll get 0.08, which is our measure of beta of the security or portfolio. To summarize, in this video, we understood the concept of beta, which is the sensitivity of security to the market movements, and a very important measure of a risk of that security. This represents the sensitivity to the security to the market movements, and therefore the contribution of the security to the portfolio risk. We also understood that this beta can be calculated by regressing the security returns on market returns, and the slope coefficient on the market variable is this beta. Mathematically, this is the ratio between covariance between security and market divided by variance of market. This is our beta for that security or portfolio. To summarize this lesson, for a portfolio with a large number of securities, only systematic or market risk that is relevant. Idiosyncratic stock-specific risk is eliminated due to diversification. When two securities are perfectly correlated, that is their correlation equal to 1, no diversification is achieved. When two securities are perfectly negatively correlated, maximum diversification is achieved. As we keep on adding more and more securities, the region of all possible risk return scenarios is obtained, which is often called feasible region. On this feasible region, we would like to go up, that is increase the expected returns, and go to the left, that is decrease the risk. When short selling is not allowed, a set of best efficient portfolios from minimum variance portfolio to maximum return portfolio are obtained that dominate all other risk profiles and often referred to as efficient frontier. When short selling is allowed, an extended feasible region is obtained. The efficient frontier is also extended to the top right. In the presence of risk-free security, a new efficient frontier is obtained, which is a tangent line joining risk-free security to the tangency point. On this new efficient frontier, the line segment toward the left of the tangency point is called the lending segment, which is a mix of investment into risk-free security and tangency portfolio. The line segment towards the right of the tangency point is called the borrowing segment, that is borrowing at the risk-free rate and investing the complete amount into the tangency portfolio.